Well, hello, friends. Today we are going to look at a security bug that someone found in Serenity. What happened was that earlier this week they had some kind of capture the flag competition, I guess, and one of the targets in the competition was a machine running Serenity. And I found this write-up that someone made here, someone named Fire30, where he basically breaks down how he found a kernel vulnerability in Serenity and used that to gain access to the machine. So I thought it was really interesting, and I got really excited that somebody thought to include Serenity in one of these competitions. So today we're just going to look at the the bug that was found, and we're going to look at the exploit and break it down, see how it works, and then look at what the bug was, and maybe like I'll show you how I fixed it, and talk about a little bit about how we can avoid these kind of problems in the future, and other stuff like that. So let's start with the bug itself. So, or rather, let's start with the challenge. So the challenge that they had was that you get a user shell on a machine running SerenityOS, and then you're supposed to find the flag, which I guess is like the object of the game is to acquire whatever the flag is. So in this case, the flag is contained in the block device dev HDB. So interestingly, we don't have, you can't just read from a block device in Serenity, at least not from user space, because we haven't implemented that yet. So in order to read from a secondary hard drive, you would have to actually call a kernel function to read directly from the device there, because there's no way to do it from user space. And he figures this out eventually here. So the bug that he finds, I mean, so the point is that I guess they're launching the machine like, normally we don't even run with a second hard drive, but if we just add one like this, foo.txt, or let's call it flag.txt. Oh no, you found me. So basically, you'd be running the machine, and now it has a secondary hard drive, which you can see, I guess, up here. This is the normal hard drive, and then we have a second tiny little hard drive that is on HDB, but we can't mount it or anything like that. So because it doesn't have a file system or anything. But I think this was the setup. So then he went looking for a bug to be able to get access to the kernel so that he could read from this device somehow. So let's look at the bug that I found. So it talks about here how we do validation of pointers that get passed into syscalls, which is how we protect against the kernel getting like a kernel or like an invalid pointer. If you pass an invalid pointer to a syscall, you're supposed to get an e-fault error, unless the pointer you pass in is like a valid pointer in that process's address space. Now, here, this is the pattern that we use in the system. So we're always calling either validate write or validate read for every pointer that's passed to a syscall. But if we, what he figures out here eventually is that the way that we validate, we end up calling this function here, region from virtual address. The first thing we do here is we check if there is a kernel region for this virtual address. If so, we'll return that region. This is used by validate user write. So this is a user space write access, calling this, and then it finds a kernel region, not a user region, and it only looks at whether it's writable or not. So this is the bug right here. The fact that we are even considering kernel regions when we are checking if a user space write access is valid. We definitely should not be doing this. So, blah, 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 and he talks about how there definitely seems to be something interesting above this address, because it's kernel-only virtual address space, right? And it turns out that we're perfectly happy to allow you to pass kernel-only pointers as syscall arguments. So as long as they are valid kernel-only pointers, which I guess makes the exploitation even easier, because you would only get an error message if you pass an invalid kernel pointer. So basically what he figures out here is that you can create these kernel read and write primitives just by simply setting up a pipe, and then if you make a write syscall to one end of the pipe, then and you pass a kernel address as the data source for the write syscall, and then you can read from the other end of the pipe, and it will have basically copied arbitrary kernel memory from one end of the pipe to the other. So that's pretty easy. So then, of course, he needs to figure out something that he actually can copy from kernel memory. So because he wants to gain code execution, I guess. So then he has to look for he looks for a stack pointer, and we very nicely, we just dump these out in the dmessage, because whenever we allocate a kernel stack for a new thread, then we printed a little message saying like, oh, I allocated a kernel thread stack for ring 0 here at this address. So you can just go and look in the dmessage output to find these. And then, as he says here, gaining code execution after you obtain a child stack base is trivial, because all he has to do is make some kind of a syscall. Like, he uses sleep in the user program, and then he can go and read the kernel stack until he finds out where that sleep syscall would return to in the kernel after blocking. And then he can overwrite that with a pointer that points to the payload of his choice, which in this case I guess is going to be a payload that reads from that device that we were looking at earlier. So then here he talks about how obtaining root and mounting the device would be enough to solve the challenge, but indeed you can't mount it because that stuff is not supported yet. So he has to read the raw block device, and so he has to call device get device to find the device object, and then he has to call this device read on it to actually read the flag. So that's basically like the rough overview. So let's go and look at the exploit. So I guess we'll clone this. Okay, we just clone it in source maybe. Oh wait, I'm not copying everything. Wait, why does it only copy part of it? Okay. Here we go. Okay, so here is the exploit, and let's just bring it into the Serenity user land directory for convenience. And we can build it there. So let's go and look at the exploit. So starting out here, what he does is he creates a memory mapping. It's a shared memory mapping, and then he creates a new process. So this is shared memory that's shared between the first process and its child, right? And then it uses that memory to communicate between the two, I guess. Let's see what he does with this. Oh, that's where he puts the flag. Okay. Okay, so he forks the child, and then I guess waits for the child to finish starting up. And then he goes looking for the base of the stack in the kernel. And the way he does that is he just opens proc the message. So I'll show you what that looks like. So if you look at proc the message here, we can see all of these. We're just printing out the kernel addresses right here in the message output. So if you're looking for the exact address of the kernel stack, you can just find it here. Very, very not cool. But it's not something that we were really actively thinking about. So, so he opens it up and then he does a get line by line until he finds something that looks like, I guess he's looking for the last instance here. Because every time we start a new thread, then we print this out. So because he knows that he just started, then he can just look for the very last one. And then close proc the message. And then apparently str to unsigned long is broken. So I wonder if that was the, maybe that was the strongest mitigation in place here. But he works around some bug we have in str to unsigned long. And eventually figures out, okay, so this is the address. So I guess if we try to run the exploit, it does not read the flag because the flag was, oh no, you found me, right? So it doesn't work out of the box like this. And it's because some of the offsets that are used here are just like hard-coded kernel function offsets. So we're gonna have to fix these to make the exploit work. But yeah, so that's the first step, is just finding the stack base based on the output from the message. And then once he has that, he looks for a hijack, which is an address on the stack that he wants to change to like steer the kernel control flow in a different direction. And the way that he finds that is that he creates a pipe, and then he writes to the pipe. This is the primitive that we were looking at up here, by the way. Where is it? This stuff right here, right? Like, so he calls write to one end of the pipe. This is a kernel address, and he writes a whole page of kernel memory to this pipe. And then from the other end of the pipe, he can read a whole page of kernel memory. And then he just reads it into this buffer here. And then all he has to do is just iterate over that buffer, looking for a specific return address, which is the one that he wants to overwrite. And in this case, if you look here, this is the child process. What the child process will do is that it will just go to sleep. And the mechanism of the exploit here is to trick the kernel into, instead of returning from the sleep and continuing here, we'll overwrite the return address and make it go somewhere else. So, so that's what he's looking for here. He's basically looking for the return address for sleep inside of the kernel. So if we go and look at the kernel disassembly and we look for the sleep, what's this called? Oh, right. This is sleep. So here, where we basically we call thread sleep, which is the blocking call. Normally, if you're not being exploited, then this call, once it returns from this function, we would resume execution here. So we can just take this address, and that should be the return address here, because that's the one that we want to overwrite. So we'll look for this address on the kernel stack and replace it with our own. So let's see. So he looks for the hijack point, and then he has a little payload. And what is his payload? Is this function right here. So he's going to make the kernel call this function. Okay. And then what this function will do is just call get device and then read from the device into the shared memory and then crash itself, because why not? Right. So then we have to look at these get device and read from device. This is supposed to be what is it called? Get device, I guess. It's this one. Yeah. So he wants to call this function, so we'll just paste this here. Oh. It's almost the same address, but not quite. And then the other one he wants is reading from a disk device. So disk device read. No, is that not it? Disk device read. Yeah, there's this one right here. So 118b10. Oh, damn it. 118b10, right? Yeah. Okay, so now we have the right offsets in the kernel that we are currently running, so that should allow us to actually run the exploit. We'll just rebuild it with these correct offsets, and we'll try to run the exploit, and ta-da! It finds the flag. Oh no, you found me. So what this did here was that it started a child process, put that child process to sleep, and then went and screwed with the kernel stack of that child process so that when it would eventually return from that sleep syscall, it would eventually wake up from sleep. Instead of going back to the normal place where it was supposed to go to return from the sleep syscall, it would instead get tricked and diverted to this payload function here. And the payload, as we mentioned, it reads into this memory here. So, and that memory is this shared mapping that we set up right here. And then we can just print it out down here. Pretty nifty. Let's see. Here we are writing. Right. So that's basically how the exploit happened. So let's look at the bug first of all. So I guess we can look at the write syscall. So when the exploit calls write, let's see. I guess here is where he actually overwrites with the payload, so this is the stuff we should be looking at. But we could actually, it doesn't matter, we can look at this too. When he's scanning the stack, then he calls write to trick the kernel into writing this memory into the pipe that he controls. So when you call write, this is the pipe that he's passing, this is the data that he wants to read, this is pointing into kernel memory right now. And normally, we call validate read here, expecting this to fail and return eFall. But if we follow the logic of validate read, then we go all the way down here to validate user read, which calls a region from virtual address and then checks if it finds a region and that region is readable. But, oh wait, hold on. Right. But region from virtual address, as we mentioned before, looks up kernel regions as well as user regions, because that's a bug. So this is where the problem happens. It allows this. So the fix for this, basically, to stop the exploit from working, is validate user read should only consider user regions. And then we have to const cast the process because of the API. Basically, this is the simplest version of the fix. So if we do only this, then the exploit will not work. Now, after this stuff landed, or after I learned about this, then I immediately went and fixed it. So let's see. Let me show you the fix that I made. So here is the initial fix. So we should reject kernel-only addresses when we validate user pointers, right? And now when we validate a user pointer for reading or for writing, we will call user region from virtual address. And then I also added an additional check here that the region is user accessible. That's just like a double check that it's not a region that's for some reason marked that it shouldn't be user accessible. And then later on, I went and also added one additional check here, just in case we make some dumb mistake in the future. Then we also do a strict number-based check, because we know that kernel virtual address user space virtual addresses should always be between the 8 megabyte mark and the below the 3 gigabyte mark. Of course, that's something that's going to change in the future. We're probably going to get rid of the bottom 8 megabyte stuff, but right now this is all valid user space addresses are in this range between 8 megs and 3 gigs. So if for any reason you pass in an address that's outside of that range, we'll just reject it without even looking at memory regions. So it's just like a little bit of extra belt and suspenders. And then another thing, or let me actually build. I guess incremental build did not work there. Sometimes it doesn't work. So another thing that was enabling this exploit was the extremely handy availability of kernel pointers in the dmessage output. So I went and, of course, I stopped printing out the stack addresses to the dmessage. And let me show you some other stuff as well. So now you cannot run dmessage unless you're root. So it's the first mitigation, if you want to call it that. And then the stack pointers are no longer printed here. Although I need to go through the code base, or we need to go through the code base and make sure that we stop leaking kernel addresses to dmessage anywhere. And really, there should not be any exposure of kernel pointers in any way that user space can see them. So dmessage normally sources its data from proc dmessage, and that's how this has been protected now. So I went and I sort of hardened the proc file system. So it used to be that everything was readable by everyone, and I went and I changed it so that many things are now only readable by root, and also you can only go into process directories where you own the process. Or of course, if you're root, then you can go into any directory. But this means that it's no longer possible to look at all the open inodes or the VM objects and stuff like that, unless you are root. And of course, you can just su to get root on the system. So I hope that's something that they removed when they did the CTF. But if you want to look at these things, you can just get a root shell. Oops, I had to be somewhere else. Get a root shell, and you can look at all of these things. So here, for example, is some kernel pointers that we need to stop exposing in the proc inodes file. And what else do we have? You can look at, I don't know, the kernel command line, stuff like that, the modules that are loaded, all of the VM objects. Here are more kernel pointers that we need to sanitize. Now, if we go into a process thing, so let's see, pgrep Windows server maybe. Oh, we don't have that. And I don't have grep either. I don't know why I think I have all these things. Oh, what's that? That's interesting. So 12, let's go to 12. This is Windows Server. So anon, the user anon is running Windows Server, but as you can see here now, I've sort of limited the access to a lot of these things that you can do here. So now you can only look at the file descriptors. That's JSON, obviously, so we should do it this way. You can see the file descriptors in your process, and you can see the VM for your process. So you can say JPVM, but this is just the user space, address space, if that makes sense. You don't see any of the kernel stuff, and then we do have the VM objects listing here, but you cannot look into it. Oh, damn it, you can. Oh, it's owned by me. Oh shit, that was supposed to be owned by root. Okay, well, there we have a bug. You can apparently still look at the VM objects. Oh shit, let's fix that right away. I thought I made that root only. Because stack and VM, I mean, so the thing is that nobody else can come into your directory, right? So the directory is owned by anon, and it's only executable by you. But I don't even want anon to be able to see some of this stuff, like the VM objects. So let's see. Damn it, give me my mouse cursor. This boolean here is supposed to mean supervisor only, so I guess I messed that up somehow. Oh. Procfs, VM objects. Wait. So we're taking off, oh shit. Oh, we're only changing the mode bits. We're not actually setting it to UID 0, so that's the bug. Metadata UID 0, gate 0. Okay, so for anything that has a supervisor only set in procfs, we should make sure that it's user ID 0. Okay, so good, we're finding more problems here. Maybe this is still Windows Server, yeah. So now VM objects is owned by root, and I can no longer look inside it. Good, it means I can no longer look at my CPU registers either. I would have to become root to see those, because, you know, they might have kernel addresses in them, so we don't want to expose that. I'm not sure if it's healthy to expose these addresses even if you are root, but right now, at the moment at least, it feels like this type of stuff is very useful for debugging the system. Maybe in the future I would want to have a mode where you can run where there's absolutely no exposure of kernel pointers to user space, even if you are the super user. I think there's probably some value in that for sure. But yeah, so this is some of the hardening of the proc file system, which we're now improving. So let's commit this. Oh wait, shit, I'm in a detached branch. Check out master. Okay, so procfs supervisor only inodes should be owned by unit 0, gate 0. Cool. So that's a nice little fix. And yeah, so this has been really quite interesting, because I was not expecting anyone to try to hack the system, and of course now it becomes very hard for the exploit to run because it can't even open proc the message anymore. So it just asserts because he assumes that it would open. So we have thwarted this particular exploit by not allowing this, and then also not allowing the arbitrary kernel memory access. So this has been really interesting, and I was really super excited to find that somebody had taken the time to make a little CTF out of the system, and that somebody actually broke it. You know, it's a little sad how easy it was, but I'm very happy that they found a bug, and I learned about the bug so we can fix it and learn from it. And you know, now I kind of want to go and try to make it more challenging for the next person who's going to try to break into the system. So I'm not really sure exactly what I'm going to do to that end, but I think that going forward, I'm going to try to you know, learn a little bit more about this kind of stuff, and try to cover some of the obvious stuff, just to just to make sure that it's not this easy to get access. But yeah, pretty neat. So shoutouts to, of course, what was his name, Fired30? Or do you have a real name, bro? Yes, TJ Corley. Shoutouts to TJ Corley for hacking the system, and to whoever ran the CTF. And thank you for checking out this video. I hope you understood the exploit and the bug and the mitigation that I've now put in place. And I hope we can learn more about this type of stuff going forward and make the system better and maybe not quite as easy to crack. So thanks for checking this video out, and I will see you next time. Bye.